Today, we're going to have a look at calculating the relative atomic mass of an element from its isotopes and the abundance of those isotopes. Both of those words will become clear in a moment. Just before we move on, a reminder that the symbol for relative atomic mass is a capital A, and a small lowercase subscript r. So that r, if I was going to draw a line to write on there, that r would be halfway between the line above and the line below. So let's think about what we mean by some of these terms. Now, there are the two most common isotopes of bromine are bromine 79 and bromine 81. You won't find these as the mass numbers if you look on your periodic tables because we've got an average mass, and I'll explain that in a moment. So bromine 79 and bromine 81, they're both bromine atoms, but they are isotopes of bromine. So they are the same element, they have the same number of protons and the same number of electrons, but they have a different number of neutrons. So bromine 81 is ever so slightly heavier. It has 2 more neutrons than bromine 79. So they're the same, they just have a different mass. Now, if I was to look at 6 bromine atoms at random, so if I were to take a sample of bromine and pick 6 of those out, then what I would find is, at random, 3 of them would likely have a mass of 79, and the other 3 would have a mass of 81. And what we can say from that is that this bromine atom with a mass of 79 has an abundance of 50%. And the bromine isotope 81 has an abundance also of 50%. What that means is, if I look at a sample, 50% of all bromine atoms in a sample will have the mass of 79, and 50% will have a mass of 81. From that, it's quite easy for us to state that the average, or the relative atomic mass, which we're saying is the average, in this case is equal to 80. Half of them have a mass of 79, half of the mass have a mass of 81. The midway point between those is 80. So that works nice and easily for bromine because it's quite a straightforward example. It doesn't work for pretty much any other isotope. So let's have a look at the isotopes of chlorine. Now, chlorine has 2 isotopes, or 2 commonly occurring isotopes, and one of them has a mass of 35 and the other one has a mass of 37. But this time the abundance is different. Let's say I was to take a sample of 8 chlorine atoms. 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to take 8 chlorine atoms. This time I would find that by random chance, 6 of those would have a mass of 35, and 2 of them would have a mass of 37. This means that the abundance isn't the same as in our last example. What we find is the chlorine 35 isotope has an abundance of 75%, or 3 in 4. So this word abundance means how much there is, how common they are. And 37 has an abundance of 25%. So this time our average is going to be a little bit more complicated to work out. We have to do what mathematicians call a weighted mean average. So let's look at how we do that. We say, first of all, that our isotope mass 35 has an abundance of 75%, and I'm going to multiply that by 75%. And we see that our isotope with a mass of 37 has an abundance of 25%. Now, to do my weighted mean average, I need to multiply the mass by its abundance and the mass by its abundance. And then I need to add those together. And then I'm going to divide by 100%. The reason I'm going to divide by 100% is my abundances all add up to 100%. So let's just break this calculation down a little bit more. So the answer to that is 2625. The answer to that is 925. Dividing that by 100, which then means I'm dividing the sum of those two, which is 3550, divided by 100, gives me 35.50. So my weighted mean average here, my AR, or relative atomic mass of chlorine in this case, is equal to 35.5. We'll talk about how many significant figures we give our answer to in the next example. So let's look at a slightly more complicated example. We're going to have a look at the isotopes of magnesium. Now, magnesium has 3 commonly occurring isotopes, and I'm going to do this as a table. So we have an isotope mass of 24, 25, and 26, and then the abundance of these isotopes is 79.0%, 10.0%, and 11.0%, and all of those should add up to 100%, which they do. So let's look at how we did that last time. I'm going to break this calculation down a little bit more this time. First of all, going to just take this bit of information here, the isotope mass and the isotope abundance, and arrange them so that we're multiplying them for our weighted mean average. So remember what we did last time is then to bracket these, and we're adding them all to each other. We should also put a large bracket around it to say that this whole sum has to be done first of all. We'll do the multiplications here, then we add these together, because at the end of it, we're going to divide everything by 100%. I'm just going to put some percents in there, just so you know what those numbers are. If we start to break this calculation down, then we find out that we've got 1896 plus 250 plus 286 all over 100%. And the percents will all cancel out actually in the calculation. And then that breaks down to 2432 divided by 100, which gives us an answer of 24.32. We need to think about how many significant figures we're going to give our answer to. And in each case up here, we had a decimal place and a 0 after it. So we're going to quote our answer to 3 significant figures, which means the AR of magnesium is equal to 24.3. Thank you very much.